right, son. Again, apologies for what happened at their last class, but regrettably, these things happen. So, what I want you to do, Hassan, is to remember we were in and off looking at the notion that alkenes are those which contain double bonds. You can see some examples here. Now, alkenes, because of the reality that they have a double bond, they are unsaturated. Unsaturated in the sense that they do not contain the max number of possible hydrogens. Now, when these double bonds form, well, a reaction can occur where these hydrogens get added back onto that. So alkenes can be hydrogenated to reform an alkane. This would consider be an addition type reaction. Similarly, another type of unsaturated hydrocarbon, which I mentioned, that being the alkynes, the one that have a triple bond, if you put excess hydrogen and expose them to, again, an addition type reaction, you can also go back to the alkane format. So with all of that being said, in terms of naming the alkenes, the first thing you have to consider is that where that multiple bond is located to, it's going to have an impact on both the chemical but also physical properties of that compound. So with that in mind, it's very important that you have to have a naming system to actually specify where that double or triple bond is located to. Now, they're named pretty much the exact same way as alkanes, but two notable exceptions. Firstly, the longest chain must contain the multiple bond, and the chain gets numbered from the end closest to the multiple bond. Now, the number that indicates the position of this multiple bond precedes the ending. For example, this compound here, it has a double bond, so therefore it's ene. We have to number it in accordance with the closest to it. The closest carbon to the double bond is this first one here. So this becomes 1, 2, 3, 4. 4 carbons, bute. The double bond begins at carbon number 1. So this is bute 1-ene. If the double bond was located here, beginning at carbon 2, it'd be bute 2-ene. Take note that the number in front of the ending specifies where the multiple bond starts. Just the same way that the number in front of a branch indicates where that side chain is located, which we looked at with the alkanes. So let's take a look, Hassan. Let's say 1 second, we'll take a look at that as well. So with that being said, how do we name alkanes? Alkenes, rather. This is how we name alkenes.
In this video, we're going to go over the nomenclature of alkenes. We're going to talk about the cis and trans isomers, and also the E and Z naming system. But let's start with the basics. So how can we name this particular alkene? Now the first thing you need to know is the common names of the alkanes, from 1 to 10. A 1-carbon alkane is known as methane. A 2-carbon alkane, ethane. 3 is for propane. 4 is for butane, 5 pentane, 6 hexane, 7 heptane, 8 octane, 9 nonane, 10 decane. So in this particular compound, we have 4 carbon atoms. So that's associated with butane. But because we have an alkene, it's going to be butene. And the double bond is between carbons 1 and 2. But you need to pick the lower number of those two, so this is known as 1-butene. Some textbooks might write it this way, but 1-ene. So you can also write it that way as well. Now what about this example? How would you name this particular alkene? So should we count it from the left side or from the right side? If we count it starting from the left, notice that the alkene is on carbon 3. But if we count it from the right side, notice that it's on carbon 2. And you want to count it in such a way that you will get the lower numbers. So this is going to be called 2-pentene since we have a 5-carbon chain. Don't forget to add the suffix "ene" for alkenes whenever you have a double bond. Try this example. Now, if we count it from the left, the alkene will be on carbon 3. If we count it from the right, it would still be on carbon 3. However, the methyl will be on carbon 5. If we count it from the left, the methyl will be on carbon 2. So therefore, we want to count it from left to right. So this is going to be 2-methyl dash 3 dash hexene. Since the double bond is on carbon 3 and a 6-carbon chain is hexane, but we got to add the suffix -ene. Now how about this example? What if we have 2 double bonds? What should we do in this case? Now we have a total of 4 carbons, which is associated with the name butane. But since we have 2 double bonds, we need to add the suffix diene for the 2 double bonds. So we have a double bond at 1 and at 3. So it's called 1,3 butadiene. The use of a comma is required to separate 2 numbers, and the use of a hyphen is required to separate a number and a letter. Go ahead and try this example. So what direction should we number it? From the left or from the right? If we start from the left, the double bond will be at 1. If we start on the right, it's going to be at 2. And the other one is going to have a much higher number. Let's count it both ways. So this will be 1, 2, 3, 4, 5, 6, and 7. That means we will have a double bond at 1 and 5. If we count it the other way, we're going to have a double bond at 2 and 6. So 1 is lower than 2, so let's count the other way. So we have a methyl on carbon 3. Let's begin with that. So this is going to be 3-methyl dash. Now we have a double bond at 1 and 5, so it's 1, 5, and it's a 7-carbon chain, so we're dealing with heptane, but instead of saying heptane, it's going to be heptadiene. And so that is the name of this particular molecule. Now what about cycloalkenes? So what if we have a double bond in a ring? How can we name it? Instead of saying cyclohexane, this is simply cyclohexene. And if you only have a double bond, one double bond in a ring, it's automatically assumed to be carbon 1. So you don't have to say 1 cyclohexene. You could just simply say cyclohexene because the double bond has to be on carbon 1. So knowing that, what is the name of this particular molecule? Feel free to pause the video as you work out this example. Now, if we choose to count it this way, the methyl will be on carbon 5. However, if we choose to count it this way, the methyl will be on carbon 3. So let's count it that way. This is going to be 3-methyl cyclopentene, since it's a 5-carbon ring. And we don't have to say 3-methyl dash 1 cyclopentene. As we've mentioned before, the double bond is on carbon 1. Now what about this example? Let's name this molecule. Now the double bond has more priority than the bromine atom in terms of naming. So we're going to start counting from the double bond. We want to count it this way. We want the double bonds to have the lowest numbers. If we start from the middle, it's just not going to work out that way. We'll have a double bond at 1, 3, and 6 as opposed to 1, 3, and 5. So this is the way we should count it. So it's going to be called 7 bromo dash, we have a double bond at 1, 3, and 5. So 1, 3, 5. And it's a 7 carbon ring, so we're dealing with heptane or cycloheptane. So it's cyclo, hepta, triene, since we have 3 double bonds. Diene is for 2 double bonds, triene is for 3, tetraene in case you have 4. Try this one. Now, in this particular example, you need to identify the longest chain, and you want the double bond to be included in the longest chain. And you want to get the double bond the lowest number, so you want to start counting here. This is going to be 1, 2, 3, 4, and this is not the longest chain. The longest chain actually contains 7 carbons. So we have a heptane, or heptene. Now, this is an ethyl group because it has 2 carbons, and this is another ethyl group. So we have an ethyl group on carbons 2 and 4. So this is going to be called 2,4-diethyl dash 1 heptene, since the double bond is on carbon 1. What is the name of these 2 alkenes? We talked about this one earlier in the video. If we number it, we could see that we have a 5 carbon chain and a double bond at 2. So this is called 2-pentene. However, if you look at the one on the right, it's also called 2-pentene. So what is the difference between these 2 molecules? Because they're not exactly the same. Double bonds are not free to rotate, and so these are actually 2 different molecules. On the left, notice that the hydrogens that are connected to the double bond, they're opposite to each other. But on the right, they're on the same side. This is the trans isomer, and on the right we have the cis isomer. So this is called trans 2-pentene, and this is cis 2-pentene. Now, for more complicated examples, where you have a lot of different substituents attached to the double bond, you may want to use the ENZ system. So first, let's determine if we have the E isomer or the Z isomer. The E isomer is similar to the trans isomer, and the Z isomer is similar to the cis isomer. Now, what you need to do is determine which group has a higher priority, and it's based on the atomic number. So if we compare bromine and carbon, you need to pair 2 groups on the same carbon atom, or attached to the same side of the double bond. Bromine has a higher atomic number than carbon, so bromine has a higher priority than carbon. Now, between methyl and hydrogen, methyl wins because carbon has a higher atomic number than hydrogen. Now, if the 2 highest priorities are on the same side, you have the Z isomer. If they were on opposite sides, that would be the E isomer, it would be trans-like, so to speak. Now, what about naming this particular molecule? What is the name for it? So let's identify the longest chain. 1, 2, 3, 4. We want to count from left to right so that the bromine atom is on carbon 2 instead of carbon 3. So this is going to be called Z, since we have the Z isomer, dash 2 bromo dash 2 butene. Now, what about this example? How can we name this particular alkene? So first, let's determine if we have the E isomer or the Z isomer. And let's make it a little bit more interesting. Let's make this a CH3. Now, you can't say it's cis or trans because you don't know which two groups to compare to. If you had two hydrogens, let's say this was a hydrogen, then you could say it's cis because the two hydrogens are on the same side. But when you have four different groups, you can't really describe it in terms of cis or trans. You need to use the E and Z system. So let's compare chlorine and hydrogen. Which of these two groups have the highest priority? Well, chlorine has the higher atomic number, so it's going to be chlorine. Now, if we compare the ethyl group and the methyl group, which one has more priority? Well, ethyl is going to win against methyl since it has more carbons. So notice that the two highest groups are on the same side. So we have another Z isomer. So this is going to be called Z. And then let's identify the longest chain. So it's going to be carbon 1, 2, 3, 4. So we have a chloro on 1, a methyl on 2. And let's put it in alphabetical order. So it's 1 chloro dash 2 methyl dash 1 butene, since we have 4 carbons total in the longest chain. Now let's try a harder example. Let's try this one. So take a minute and see if you can name this particular alkene, including with the E and Z system. Now the first thing I would do is identify each alkene as being, each double bond as being E or Z. So let's draw the hydrogens that are located on each of these double bonds. So if we compare the hydrogen and the methyl group has more priority. And if we compare chlorine and this group, so you're looking at the carbon atom first versus the chlorine. Chlorine has a higher atomic number than carbon, so chlorine has more priority. So the highest groups are on the same side, therefore this is the Z isomer. Now let's focus on the next double bond. On this side of the double bond, we're comparing the methyl and the ethyl group. The ethyl group wins because it has more carbons. And on this side of the double bond, we're comparing the hydrogen compared to this, and hydrogen always loses, with the exception of comparing it to another hydrogen atom, which will be pointless. So this side has the higher priority. So notice that this is the E isomer. For it to be the Z, these two would have to have the highest priority, or these two, because those would be on the same side. But these two groups are on opposite sides, so we have the E isomer. Now let's put it together. So let's identify the longest chain. We want to count from left to right so that the first alkene will have a number of 2 instead of 3. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8. Now the double bond at 2 is associated with the Z isomer, so we're going to put 2Z. And at 5, it's associated with the E isomer. So if you have 2 or more double bonds, you need to put the number next to the E or Z letter to specify each double bond and its specific stereochemistry, so to speak. Now we have a chloro group on 3 and a methyl on 6. So let's put it in alphabetical order. It's going to be 3 chloro dash 6 methyl dash, we have a double bond on 2 and 5, so 2, 5 dash octa, since we have a total of 8 carbons, octadiene, since we have 2 double bonds. And that is it for this video. Thanks for watching and have a great day.
Okay, Sans, that video gave an overview of the naming of the alkenes, looked at a number of the other aspects of it. To that end, continuing on our examination, remember, when we're looking at these aliphatic hydrocarbons, the alkenes double bond named as per that video. As for the alkynes, one of the significant things here is that the alkynes, not a lot different, except now, a lot of rules are the same. It contains one or more triple bonds. And because you've added another unit of unsaturation, you're taking away another 2 hydrogens. So the general form is C to the N, H to the 2N minus 2, but this is applicable only if you have a 1 triple bond. Now, because it's unsaturated, well, carbon atoms, hydrogen atoms, other atoms can be added to this structure without taking something away. If you're going to put something on an alkane, something's got to come off. It's already saturated. So when you're naming alkenes, when you're naming alkynes, start with the parent chain that has to contain the multiple bond. If it's a double bond, ene. If it's a triple bond, ine. You count the carbons so that the multiple bond will be on the lowest possible number. You indicate that number the multiple bond falls on before the prefix and add the branches before. For example, but1-ene, but2-ene. In both cases, the multiple bond starts, in this case, at carbon 1 versus carbon 2. This one here, a triple bond, same thing. Longest continuous chain that contains the multiple bond, in this case, be a 5-carbon chain. You number the carbons so that the lowest number is attached to the beginning of the multiple bond. In this case, that will be carbon number 2, which means you have a side chain located at carbon number 4, a 1-carbon or methyl group. To name this, it would be ine for the triple bond, 5-carbon pent, multiple bond beginning at carbon 2, pent 2-ine. Side chain at carbon number 4, a 1-carbon, 4-methyl, pent 2-ine. Now, in the case of methylpropene, well, you don't really need a number because there's only one option for it. It has to be a carbon number 1. No matter where you put it, it's going to be carbon number 1. So again, multiple bond, 3-carbon, double bond, ene, propene, side chain at carbon number 2. So methylpropene. Taking a look at this one, same principle. We have a double bond. We know it's ene. Longest chain containing the side chain, 4 carbons. 1, 2, 3, 4. Numbered so that the double bond is given the lowest number possible. Carbon number 1. So but1-ene. Side chain at carbon number 3. Therefore, 3-methyl. But1-ene. Same thing here. Longest continuous chain that contains a side chain. 1, 2, 3, 4, 5, 6 carbons. Hex-ene. We number it so that the lowest possible number is found that includes it, which means that 1, 2, 3, 4, 5, 6. We have a side chain, a 1-carbon side chain located at carbon number 5. Therefore, 5-methyl, hex for the 6 carbons, 2-ene. Now, is it possible for a molecule to have more than one double bond? Of course it is. These are alkadienes, di meaning 2, and they're going to remove 2 more hydrogens, 2 hydrogen removed for each double bond that you put in place. So if we have buta-1,3-diene, 4-carbon with 2 double bonds, beginning at carbons 1 and 3 respectively. Carbon 1, double bond, 3, double bond. Buta-1,3-diene. Naming this one, 1, 2, 3, 4 carbons, 2 double bonds, a diene. Double bonds begin at carbons 1 and 2 respectively. Therefore, buta-1,2-diene. You would follow the same principle for alkynes. We've already gone through cyclo or ring compounds, same principle. It's a ring structure, so you have to add cyclo. Now, the numbering, again, is going to begin, where's the double bond located to? You give it to the lowest possible number. So if you were to draw 3-methyl-cyclohexene, well, 6 carbons in a ring. We give the double bond the lowest number, so where the double bond begins must be carbon 1. So 1, 2, 3. Right, carbon 3 is a 1-carbon side chain, hence 3-methyl-cyclohexene. Now, what we do see is that molecules get bigger. You'll notice that the boiling points and the more carbons involved increase accordingly. One industrial process used to split alkanes down is a process known as cracking. That's very prominent in the industrial age. So just shifting gears here a little bit. So when you have these large molecules such as pentane, it's cracked or broken by adding hydrogen to actually split these apart through chemical processes. So before I do that, let's take a look now at how to name alkynes.
In this video, we're going to focus on naming alkynes. So let's begin with the common names. How can we name this particular alkyne? This is C2H2, and its common name is acetylene. Now, this is also called ethyne because it's an alkyne, so it ends with the suffix -yne. But the common name is acetylene. Now, let's try another example. What do you think the common name is for this molecule? So here we have the acetylene portion of the molecule, which is the C triple bond C part. And notice that we have a methyl group in front. So therefore, the common name for this alkyne is simply methyl acetylene. So based on that example, go ahead and try this one. So write the common name for this molecule. So let's focus on the acetylene portion of the molecule. And notice that we have a methyl group on the left and on the right. So therefore, this is going to be called dimethyl acetylene. Dimethyl acetylene. And so hopefully you're getting the hang of how to write the common names of alkynes. Now let's move on to our next example, which is going to be CH3, CH2, C, triple bond, CH. So go ahead and write the common name for that alkyne. And also write the IUPAC name, since we're here already. Let's go ahead and do that. Let's start with the IUPAC name actually. So this is carbon 1, 2, 3, 4. So 4 is associated with butane, but instead of writing butane, we're going to write butyne. Now the triple bond is on carbon 1, so this is called 1-butyne. Now what is the common name of this particular alkyne? So we can see that we have our acetylene group, and this is an ethyl group attached to it. So the common name is going to be ethyl acetylene. And so that's it for this example. Here's another one. So for this example, write the IUPAC name and also the common name of this particular alkyne. So let's start with the IUPAC name. We need to number in such a way that the alkyne has the lowest possible number. So this is going to be carbon 1, 2, 3, 4, 5. So that's pentane, but instead of saying pentane, it's going to be pentyne. Now the triple bond is between carbons 2 and 3, so we have to pick the lower of those two numbers. So this is going to be called 2-pentyne. Now let's try the common name. So here is our acetylene functional group. And on the left side, we have a methyl attached to it. And on the right side, we have an ethyl group attached to it. So we need to put it in alphabetical order. So the common name is ethyl, methyl, acetylene. Now, for this next example, all I want you to do is to write the common name. So let's say that we have a benzene ring attached to the carbon-carbon triple bond. How can we name it? So notice that whenever you have a benzene ring as a substituent, it's called phenyl. So to name this, it's simply going to be phenyl acetylene. And for the common name, you need to write it as one word. So if you see me put a space, it really should be together as one word. So just keep that in mind. Now let's work on another example. So for this one, write the common name and the IUPAC name as well. So let's start with the IUPAC name. This is going to be carbon 1, 2, 3, 4, 5, 6. So we have a methyl on carbons 2 and 5. So it's going to be 2,5 dimethyl. And for 6 carbons, that's hexane, but we're going to use hexine. And the triple bond's on carbon 3. So it's going to be -3 hexine. And so that's how you can name this particular alkyne. Now, what is the common name for this particular molecule? So notice that we have an isopropyl group on the left side and on the right side. So this is going to be called diisopropyl acetylene. Now let's work on one final example. What's the common name for this molecule? So we have 2 phenyl groups attached to the acetylene part. So it's simply going to be diphenyl acetylene. Now let's work on some more examples with IUPAC nomenclature. So go ahead and write the IUPAC name for this particular alkyne. Now, should we number it from left to right or right to left? If we go from right to left, the triple bond will be on carbon 3. And if we go from left to right, the triple bond will still be on carbon 3. So which way should we go? Going from left to right, we're going to have the name 2-chloro. And then we have a methyl group on carbon 5. So it's going to be 5-methyl. And we have the alkyne on carbon 3. So that's going to be 3-hexine because we have 6 carbons in the parent chain. Now, if we go in the other direction, this will be 1, 2, 3, 4, 5, 6. So chloro still comes before methyl. We still need to put it in alphabetical order, but it's going to be 5-chloro 2-methyl 3-hexine. And so the first one is going to win because you want the first substituent to have the lower number. And so this is the right answer. Now let's move on to our next example. So it's going to be CH3, CH2, CH with a CH3 attached to it. And then we have our carbon-carbon triple bond. And another triple bond at the end. So go ahead and name that molecule. So because we have the triple bond at the end here, we want to start counting from right to left. We want to give the triple bond the lower values. So we have a 9-carbon chain. That's the longest chain. And so that's going to be nonane, but instead of nonane, it's going to be non-9. We do have 2 alkynes, or 2 triple bonds, so it's going to be a diene. So let's put it all together. We have a methyl group on carbon 7, so it's 7-methyl, and then we have a triple bond at carbon 1 and 5, so it's going to be 1, 5, nana, and then diene, because we have 2 triple bond functional groups. And so this is how we could name this particular molecule. Now, what do you do when you have a molecule that contains an alkyne functional group and an alkene functional group? Which one has more priority? Should we place the one at the alkyne or at the alkene? In a situation such as this, the alkene has more priority. So we're going to count, giving the alkene the lower number. So we have 6 carbons. So this is hexane, but it's going to be hexene instead. Now the way you name it, it's going to be 1 hexene, because the alkene is at carbon 1, and then dash 5-ine, because the triple bond is on carbon 5. And so that's how we can name a molecule that has an alkene and an alkyne functional group. Now, what if we have an alkyne with an alcohol functional group? Which one has more priority, the alcohol or the alkyne? It turns out that the alcohol has a higher priority than the alkyne. So we're going to give the OH group the lower number. So this is called 3-butyne, because the alkyne is on carbon 3, and then dash 2-ol, because the alcohol is on carbon 2. And so that's how we can name this molecule. Now let's try one more example. Go ahead and name this particular molecule. So how should we count it? Should we count it like this? 1, 2, 3, 4, 5, 6, 7, 8? Or should we count it like this? 1, 2, 3, 4, 5, 6, 7. When you count the longest chain, it has to include the alkyne functional group. So we need to use the numbers in green. So this is carbon 1, 2, 3, 4, 5, 6, and 7. Now we have a propyl group on carbon 3. So this is going to be called 3-propyl dash 1 heptine, since we have a 7-carbon chain with the alkyne functional group, and the triple bond is at carbon 1. And so that's it for this video. So now you know how to name alkynes using IUPAC nomenclature, and you know how to write the common names for alkyne molecules. Thanks for watching.
So again, that's how we name alkynes. Again, the big thing with alkynes and alkenes, they have multiple bonds. Alkenes, a double bond, at least 1 carbon-to-carbon double bond. An alkyne has at least 1 triple bond, carbon-to-carbon triple bond. They're unsaturated, meaning they could contain more, but the double bond's there. So to convert them to saturated, you can have addition reactions, adding hydrogen. An alkene can be reduced down accordingly. Now, naming it, number the longest continuous chain, contain the multiple bond, identify the type and location of each branch, use the format we've talked about, and remember, isomers are alkenes of cycloalkanes, and alkynes are isomers of cycloalkenes. And when these are broken down, that's certainly something that's key and integral to the petrochemical industry in Alberta. This brings us to the next group, that being the aromatics, subsequently called because they actually have strong smells. That's where they got the original name. What they involve is they involve a unique structure, which is known as a benzene ring. Now, what happens at the benzene ring is that they are structures, a 6-carbon ring structure that has a delocalized set of electrons that are shared between them all. The formula for this benzene ring is going to be 6 carbons and 6 hydrogens, delocalized going around. So you could consider it in terms of chemical structure to have an alternating pathway of double bonds all the way around, but it's not really localized between any of the carbons. They're equally shared between all of them. Because of that universal sharing, that makes the molecule very stable because it is shared equally. It's more stable than alkenes. It's very equal to split. And coincidentally, benzene's a known carcinogen. It's actually in petroleum. So you have to be careful around these things. So take a look at what we mean by the idea of aromatics and cyclic compounds.
We've talked up carbon quite a bit here on Crash Course Chemistry, but we really haven't justified the lofty position I put it in. Just chains so far, and while chains are good, they're not enough reason on their own for this high level of esteem. But carbon atoms, they do more than just form chains. Sometimes they form rings, or as chemists call them, cyclic structures, and if the rings have the right number and placement of double bonds, they start acting weird and wonderful. The compounds made from them are called aromatic, literally because they have aromas. They can smell amazing. Basil, vanilla, cloves, tarragon, lemon, cinnamon. When we smell these things, it's because aromatic compounds with carbon rings, are binding to receptors in our noses that tell our brains, OMG, tasty stuff nearby. Of course, mothballs and modeling glue and lots of other stuff are also aromatic and don't smell so good. But if you've ever smelled an herb, taken medicine, worn clothes, or enjoyed a meal, you probably owe that experience, at least in part, to aromatic hydrocarbons. But before we talk about aromatics, let's talk about the most basic cyclic structures, the cycloalkanes. You recognize the alkane ending there, so there must be no double bonds, right? And you can't make a ring with 1 or 2 carbons, so the simplest cyclic hydrocarbon must be cyclopropane. But those tight bond angles of that triangular cyclopropane make it very fragile. This instability makes it highly reactive, and it would much rather just be a straight chain. But as more carbons join into the ring, cyclic structures get more stable. Cyclobutane with its 4 carbon atoms is still fairly unstable and reactive, while in cyclopentane, the bonds are even more stable because they form something close to those tetrahedral bond angles, while the bond angles in cyclohexane are basically perfect for the tetrahedral orbitals to overlap without strain. Cycloalkenes also start at 3 carbons and get increasingly stable as more are added, though their double bonds make their molecules planar instead of tetrahedral. Finally, cycloalkynes do exist, but they are crazy hard to form because the triple bond is linear, so it hates bending into rings, and that is why the simplest cycloalkyne has 8 carbons. Of course, these rings can have all sorts of things stringing off of them, and their names work almost exactly the same way as straight chains do. Example: this ring has 5 carbon atoms in a double bond, so it's a cyclopentene. It has 2 branches, an ethyl group and a methyl group. We list these in alphabetical order in the name, and we number the carbons in the ring so that we get the lowest possible numbers on the branches and on the double bond. If we number counterclockwise from the beginning of the double bond, we get the branches at the 2 and 5 positions, but if we number clockwise from the double bond, the branches are at the 1 and 3 positions. So this must be 1-ethyl 3-methyl cyclopent-1-ene. But since there's only 1 double bond and it's in the first position, the second one is often left out as being understood, so we simply call it 1-ethyl 3-methyl cyclopentene. Incidentally, all of the identifying parts of an organic molecule, the double and triple bonds, the carbon chains that branch off the main chain, those are called substituents because they substitute for hydrogen atoms. So far, we've just been looking at the cyclic hydrocarbons. So what's up with the aromatics? How are they different? Well, this is one of those times when carbon starts doing some of its spectacular dances. Cyclic hydrocarbons that contain resonance structures. Things are getting interesting. And by interesting, I mean What? Resonance occurs when electrons are distributed around the molecule in a way that makes it impossible to draw with a single Lewis structure. It's a limitation of our tools to represent the beauty and complexity of reality. In a resonance structure, the real-world structure of a molecule is essentially an average of all of the possible structures that we can draw. The simplest aromatic hydrocarbon, and one of the most common, is benzene, C6H6. It's the pungent compound that gives gasoline its strong, sweet smell. It contains 3 double bonds, so that each carbon has a total of 4 bonds. We normally write this and other organic structures without the hydrogens in order to simplify things, and we often don't even write the C's for the carbons. Every corner is assumed to be a carbon atom, and since we know that carbon needs 4 bonds, it's easy to figure out where the hydrogens belong even when they're not written. Here's the thing though. Those double bonds could just as easily be in these positions, and they are in those positions. Sort of. Remember, there are 2 types of bonds in double bonds. There's those sigma bonds that happen linearly, and then there's those p orbitals that stick up above and below the plane of the molecule. Those p orbitals in an aromatic compound all merge together in a ring that stretches above and below the whole molecule. It's a distribution of electrons that's like a donut on top of and below the molecule. It's extremely stable. Overall, the bonds are in both places, so the actual structure is essentially an average of the 2 drawable Lewis structures. That's resonance. It's reality poking us in the nose and saying, oh, you thought you were so clever with your Lewis structures, but in this situation, they are useless. To show that the double bonds aren't in any specific place, we often just show the structure with the circle in the middle, signifying that the double bonds are averaged in a ring throughout the benzene group. Technically, the number of bonds between each pair of carbons is defined as 1.5. It's not a double bond, it's a 1.5 bond. Now, aromatics can have all sorts of substituents as well, and the naming system is pretty much the same as with other cyclics. Another example. So this is a benzene with 2 methyl groups on it. As always, we number the ring so the branches have the smallest possible numbers. In this case, if one of the methyl groups is in the 1 position, the other is in position 2. Note that the numbering could also be done like this, but it doesn't matter as long as the branches are at the lowest possible numbers. That makes this molecule 1,2-dimethylbenzene. Now, if you swap the methyls out for a couple of other slightly more complicated groups, then you get acetylsalicylic acid, or aspirin. Aromatic rings can be used the other way around too, as substituents onto hydrocarbons. Check out this molecule, a hexane with a benzene ring attached to carbon number 2. When benzene is used as an attachment, we call it a phenyl or phenyl group, so this is 2-phenylhexane, or 2-phenylhexane. It doesn't matter. What's important is that it is not a benzyl group. Why? Well, it was English genius Michael Faraday who first isolated benzene in 1825 from the gas used in lamps, and in honor of this, his French contemporary chemist Auguste Laurent started calling the derivatives of benzene phen, from the Greek for I illuminate. It's a lovely gesture, very sweet, but like, seriously? But just to make sure you're like good and solidly confused, benzyl groups do exist. They're a phenyl group joined by a methyl group instead of just directly. So now that we know where the word phenyl comes from, I bet you're just salivating with curiosity wanting to know where benzene comes from because, like, your desire to know things is stronger than any of your other desires, right? Yeah, I thought so. So here's how it happened. Back in the 1400s, when the spice trade drove the majority of the global economy, Arabic traders sold European traders a resin used in perfumes and medicine that they called Lubanjawi, or Ensigns of Java. Of course, it didn't come from Java, it came from Sumatra, but the world was a big and complicated place, so we can't really blame them for being a little bit confused. The Lu was mistaken by the Italians for the definite article la, and so it was dropped, making it Banjawa, and then the French called it Banjois, and eventually the German and English made it benzoin. This is also, by the way, the same root as the name Bon Jovi. It's not. When we started doing some chemistry, we found that most of benzoin was composed of an acid which chemists named benzoic acid, or acid of benzoin. Then, a little chemistry knocked the acid off, creating what was clearly an alkene, so they named it benzene, because it was an alkene that was from the benzoin resin. History is hiding everywhere, and so is chemistry. Now, benzoic acid is one of literally infinite possible benzene-based compounds. There's naphthalene, the main ingredient in mothballs. It's basically 2 benzene rings stuck together. And there's anthracene with 3 benzenes, which is probably the dye that's making your blue jeans blue, and it can get crazy complicated all the way up to humic acid, a component of soil. Now you might be wondering how something so complicated as that could ever even come into being. Like any organic compound, aromatics can undergo tons of reactions that produce all sorts of molecules. By far the simplest and most common are substitution reactions, in which one substituent is substituted for another. Like one of the hydrogen atoms on a benzene might be changed to a propyl group, or then a halogen might come in and replace that propyl group with a bromine. These changes alter the compound, of course, but it may not be that major a change. Like, changing your shoes, unless you put on some really weird shoes. Another fairly common reaction of aromatic hydrocarbons is coupling, the joining of two aromatic structures, and it basically works the same as a substitution reaction. The only difference is that the new substituent is another aromatic structure, and it typically requires some kind of catalyst. A final common reaction of aromatics is hydrogenation, which we talked about a little last week, the addition of hydrogen atoms to remove double bonds. Now, of course, getting rid of even a single double bond in a phenyl group always destroys the resonance, and thus it is no longer an aromatic compound after hydrogenation. Now, obviously, we haven't covered all of the possibilities here, but you can already see that organic molecules have the potential to become extremely large and complex, integrating straight chains, cyclic structures, and aromatic groups in the same molecule. This literally infinite variety is what makes organic compounds the basis for the infinite variety of life on Earth. So I'll leave you to your genes and basil pesto and aspirin now to appreciate them on a whole new level that simply was not possible just 10 minutes ago. Meanwhile, thank you for watching this episode of Crash Course Chemistry. If you paid attention, you learned about the structure of cyclic organic compounds and how to name them and their substituents. You also learned what an aromatic compound is, what resonance is, and how to name aromatics and their substituents. And finally, you learned a few common reactions.
So that outlines the notion of what alkynes are. We talked about benzene or the aromatic. Again, just to illustrate this, just look at once again. Its formula is C6H6. It's unreactive. It doesn't have any true double or triple bonds. It actually delocalizes electrons. Each of the bond lengths are equal in length and strength with bonding to a hydrogen. So it looks like it really is represented by this type of structure. A 6-carbon ring with a circle in the middle, indicating that there's resonance, indicating that the electrons are delocalized and shared equally between all of the carbons involved in the structure. So some common compounds: aspirin, vanillin. Often we see condensed formulas. Actually, look at the benzene ring. We see this here. Aspirin, acetylsalicylic acid, vanillin. Other examples. Again, notice that they all contain this benzene ring, this aromatic ring in the middle. Now, sometimes benzene rings are attached as a branch. In that case, they're given the name phenyl. This one here, 3-methyl-3,5-diphenylhexane. The root is hexane, a 6-carbon chain, all single bonds. To this 6-carbon chain, we have side chains, a methyl group and 2 phenyl groups. Hence, it's named 3-methyl-3,5-diphenyl. Because M comes before P, that's why the numbering system is done as it is here. Now, if the alkyl branch is attached to a benzene ring, the compound is named as an alkyl benzene. For example, this here, we have the benzene ring as a branch of a large molecule. In this case, it's a phenyl branch. Now, this is an alkyl benzene. This one here contains a phenyl branch, not terminal, in the middle. These side chains, in this case, so this would become 1-ethyl, 2,5-dimethyl, or 2,4 rather, dimethyl benzene. So again, just to recap, in naming, if there's more than one alkyl branch, the branches are numbered using the lowest numbers possible, starting with one of the branches. If you have a bigger choice, such we see here in this example, choose the set that is both numerical and alphabetical order. This one here, 1-ethyl, 2,4-dimethyl benzene. Conversely, because this is not a side chain, part attached to a longer chain, an 8-carbon single carbon chain, octane, attaching the numbers, this would be 3-phenyl, 4-propyl. Propyl, a 3-carbon chain, propyl. So 3-phenyl, 4-propyl, octane. So if we're to draw 1,2-dimethylbenzene on carbon 1 and carbon 2, 2 methyl groups attached to a benzene ring. Also, in this 1,2 arrangement, sometimes referred to as ortho. 1,3, meta. 1,4, para. So you see the structure. 1,2-dimethylbenzene, some refer to as ortho-dimethyl. 1,3-dimethyl, meta-dimethyl. 1,4-dimethyl, para-dimethyl. So let's take a look at this one. The line structure for 1-ethyl, 3-methyl. Here we see it. A benzene ring with a side chain, an ethyl side chain, a 2-carbon side chain, a carbon number 1, and a carbon number 3, a 1-carbon. Here, the benzene ring is not located at a terminal carbon. So we have this 5-carbon alkane, pentane, of which at carbon number 2, we have a phenyl group attached to it. Hence, 2-phenylpentane. So we can look at these. Again, take note, because it's a side chain with a double bond at carbon number 2, this would be 3-phenylpent-2-ene. Here, because it's on the beginning, propylbenzene, no numbers needed, there's only one side chain, propylbenzene, and all the carbons are equivalent. Now, is there a mistake here? Well, double bond isn't there? This wouldn't be CH2, CH2. This would be CH2, CH. Because of 2, this is 1, 2, 3. Double bond. Double bond, so it must be a CH. So when naming aromatic hydrocarbons, if it's attached to a benzene ring, the compound named is an alkyl benzene. Alternatively, it can be a branch if it's in a larger molecule. Benzene is called a phenyl branch. More than one alkyl branch, the branches are numbered using the lowest number possible, starting with one of the branches. Given, if you have to make a choice between lower numbers, choose a set that's both numerical and alphabetical order. Okay, as we see here for this one. 1-ethyl, 3-methyl. 1-ethyl, 3-methyl. Using the alphabet to decide. So in summary, we've looked at aliphatic, we've looked at aromatics, and you need to be comfortable with the hydrocarbons. They fit aromatics or aliphatics. With the aliphatics, the alkanes, the alkenes, alkynes. Single, double, and triple bonds respectively. Thanks for your attention. We'll see you in class.